This is Dr. Brothers with ECE 3872 Design Fundamentals. And this lecture is going to discuss hardware design. So the design process that we're going to go over today is going to look at the V design process, top-down design, bottom-up implementation. So the first stage of this is customer discovery and needs analysis. This is where we're going to look at what the customer actually wants and what we can do to satisfy those wants. After that, we're going to do a decomposition and design process where we take the requirements and decompose that from the system level view to the subsystem to the component level view. So we're going to take this big problem and break it up into smaller and smaller problems until we finally get down to something, the component, that we can build and test. That's what we're going to do next, is build and test the components. Then we're going to integrate the components into subsystems and test those. Integrate the subsystems into the system and test that. At any point in this process, we can cross over the V and go back down it again. If, for instance, something fails a test, we'll cycle through the process again and do it one more time. So the system engineering design process, ISO 15288, formalizes this process. So at the very top left, we have stakeholders, requirements, definitions. Then we do the requirements analysis, the architectural design, then we implement the components. So in this formalized process, we have system, subsystem, and component level design, and this whole process is driven by documentation. There's requirements documents, design documents, test documents, software documents. There's documents to document every stage of this process. There's also testing. Each of the lower stages are verification tests. Then at the very top level, we validate the design. So we are validating that the design meets the customer needs. We're doing verification to show that what we have built is what we intended to build. So that's the difference between validation and verification. Verification, you're just making sure that what we built is what we meant to build. And then validation is we're making sure that what we built actually addresses the customer's needs. So the design process, customer discovery and needs. We need to look at what the customer is actually wanting. What need would the product fulfill? Is it driven by market forces? Is it a social need, such as the need for clean water? Artistic need? Who are the stakeholders? Who does this matter to? Basically, who's your audience when you're making these discussions? System decomposition, we take all that idea and we take requirements and we drive them down into something that we can actually build to. So our requirements have to be functional, performance, safety, interface security, all these things are balled up in the requirements. So the requirements that we're building for our system based on the customer needs must be testable and they must be precise. So once we get the system level requirements, we're going to continue to break those down, decompose those further into subsystem and then component level breakdowns. Together, these will form the basis of the entire system. The requirements, you need to identify the needs from the stakeholder. Oftentimes, the customer has no idea what they actually need. You know, if you, I think it was Henry Ford once said that if you asked a man what they wanted, they would have said a faster horse instead of an automobile. That's the same thing. So our job is to interpret the needs of the customer and determine how to address those needs. So we're not always going to build exactly what the customer thinks they need, but we're going to build what suits their needs. So this illustration, tire swing, is one that has been around for so long, and what the customer wants is a tire swing. All these other people are interpreting things in different ways. This process that we're teaching you is intended to help eliminate the tire swing problem by making a document-driven process where everybody is fully informed about what's being built. And it's not so easy. This is from Office Space. I take the specifications from the customer and bring them to the engineer. That's not all it is. There's really a lot of work in this stage. Requirements decomposition. Each requirement must be traceable. As we go down through this decomposition, we need to see what the customer need was, and then how did that go into the system requirement, the subsystem, and the component, and how do they trace back up? They also must be testable. So here are some forms of test. We can do inspection tests. That means that I'm going to look at something. So one of the requirements in the project that we're doing this semester is that the design can't have any sharp edges. So this is easy to pass via inspection. We're going to look at the product and see if the edges are sharp, see if there's anything that is a safety risk. Demonstration. This is when we actually take a system or a subsystem or a component and we operate it just to demonstrate some type of compliance. For instance, say that there's a requirement that says we need an LED that turns green once the power is applied. Okay, we can turn on the power. Once the system comes up, the LED turns green. We've demonstrated it. We're done, we move on. Test is the other form of verification of a requirement. Test, you're going to actually use some equipment to measure and prove that the requirement has been met. For instance, this year in our project, there is a requirement that says that the output must be within plus or minus 1 hertz of the input. That's something that we're going to have to measure. We're going to have to take an oscilloscope. We're going to have to take a signal generator. We're going to put a signal into the box. We're going to get an output onto the output scope. We're going to check that it is within plus or minus 1 hertz to test this requirement. And we'll have to do that for all the combinations of the inputs to prove that this requirement has been met. So here's an illustration of how this is done. We first start off with the customer needs, and they don't really know what they want. They just have some idea. So we need to analyze those needs, and then we start with system requirements, subsystem requirements, components. Now, obviously, in order to do this breakdown where we're going to take it and go from the system to the subsystem to the component, we also, in parallel to all this, we also need to do the architectural structure to know what is our system, what are the subsystems, what are the components. So these two tasks are happening in parallel because as we develop the requirements, we're also developing the architecture. So these go hand in hand. We're also developing the tests. So all three of these, how you're going to test it, what you're going to build, and the requirements that drive that, these are all being developed at the same time, and they work together to reinforce each other. So if you don't know the architectural decomposition the hierarchical decomposition of your box, you don't know the system, you don't know the subsystems, you don't know the components. You can't develop requirements for those. If you can't develop requirements, you can't test to the requirements. So all three of these are developed in parallel and at the same time all through this design process. So here's an example of how we can take a customer specification, a customer need, and create some requirements from that. So the first thing we're going to do, we're going to number everything. So this is specification number 10. Apparently there were 9 before this, and there's probably more after this. And this says, create an interesting user interface. What does that mean? What does that mean to an engineer that's trying to build something? What is interesting? We can't test interesting. So what we're going to do is we're going to try to break that into a set of requirements that are testable in order to meet the customer's needs. So for instance, requirement number 1, system level requirement number 1, we're going to put push buttons on it, and then we're going to distribute them in an artistic manner. So is this testable? It's still a little hand wavy, but you know, we're getting closer. So we're going to do an inspection test on this to look at it and see if the distribution of the buttons are pleasing to the eye. System requirement number 2, the push buttons are connected to colored LEDs to generate a pattern of colors. Okay. Generation of colors with the pushing of a button. I'd say that qualifies as interesting. That's a conversation that you have with the customer. Make sure that they agree on your interpretation of their word interesting. But now we have something that's testable. So we said when we push the push buttons, colored LEDs are going to generate a pattern. Okay, we're going to generate that. We're going to push the button and we're going to see a pattern of pretty LEDs happen. That's testable. We can get a pass or fail from that requirement much more than we can get from create an interesting user interface. Requirement number 3. Each push button is connected to 2 tones, a high tone and a low tone. The selection of the tone is dependent on a high-low selection push button. This system that we're designing in this example is a musical sculpture. And so when you push the buttons, it's supposed to create musical notes. So by this requirement, we are now starting to really hone in on how this particular instance of the design is going to create musical notes. And they're going to be created by each button being connected to a high and a low note. And then there's going to be another push button that's going to select whether or not it's going to be the high or the low note when you press that push button. That's a test. We're going to actually test those and take measurements. We're going to have a test matrix. We're going to say, okay, I'm going to push this button. What tone came out? Record it. I'm going to press the high-low selector button. What tone came out? Record it in the table. Measure these and quantify them. System requirement number 4, there's going to be a total of 5 push buttons that will be used to produce 8 tones, 4 tone buttons, and 1 high-low button. In this manner, the user can play the sculpture like a musical instrument. Remember, all this is derived from an interesting user interface. But there was another user requirement that it play 8 tones. So both of those requirements can drive into this one system requirement. So there's not a one-to-one mapping of user needs and requirements. One user need might produce a whole bunch of requirements, where another user need, we might just incorporate it into an existing requirement. So we are going to restructure the requirements as they are applicable for our product. Then there's a test plan section. And so we are now going to have a test plan document. And this is calling out in that test plan document where you need to go to find out information about these specific tests. Now, after we get that, that's a system level. Now we need to decompose it into the subsystem and the component. So the subsystem, at the bottom of the slide, the parent requirement is system 1.3. We can look up at this table. I'm sorry, that's a typo. That should be system 3. So system 3, each push button is connected to 2 tones. That is devolved into a child requirement, which is processor 1.1. And in processor 1.1, this is the processing subsystem. And it's going to go in there and it's going to say the push button selection will encode to a unique identifier for the tone. So now we're seeing where the processor, what the processor is going to do with the push button selection. This would be further refined in a component. And in that component requirement, it would actually go further into detail to say the encoding would be of the form, and it would have some type of a table so that everybody can know that tone 1 corresponds to such and such hertz value. So this is how we want to do the requirements analysis in order to be able to split this very large problem up into smaller and smaller problems that we can then distribute to team members and build. How do we actually do that? How do we actually distribute it out to all our team members and build it? So we've already been talking about how to do this first stage. And then we do the system architecture. That system architecture is what I'm talking about, the system, the subsystem, the component. We're going to design these 3 levels. These 3 levels will include some form of software, some form of electrical, and some form of mechanical. So on the software side, we're going to have the software specification, the software architecture, the software design, and the software code finally resulting from that. Oftentimes in the software design, we'll use a software framework, which is what we call skeleton code. And so it might connect together all the functions in order to give us the architectural representation. But there's no code body. There's no function, and there's no code inside each function call. It's just how the code's going to be tied together. Then you can distribute to all the programmers to fill in the functions. Electrical, it's done much the same way. We start out with the electrical spec, the electrical architecture, and then we do the electrical design. That design will include part selection, schematic, PCB layout. So we might have a power board, we might have an analog board, we might have a digital board, we might have a whole bunch of PCBs that need to be designed and laid out and built. That's the last step, is the electrical fabrication. The PCB layout is connected to the mechanical design because that's how we're actually connecting the two together. The PCB will have standoffs that mount to the mechanical design, and the hole pattern needs to line up between the two. So there needs to be communication between those 2 design stages. Once all these are built, we're going to integrate them, and then we're going to do the system verification. Now, all the while, that should actually be system validation. All the while we're doing verification testing through this entire process. Once we build it, we do another verification, and then we actually do the validation to make sure that it is what the customer is looking for. The design flow. Hardware design is a combination of electrical and mechanical design. So we need to handle the communication between all of these different software tools that enable us to do the design. And we need to make sure that there are artifacts that are produced, such as the schematics, the Gerber files, the 3D drawings. All of those need to be combined in some way so that we make sure that everything lines up. In a perfect world, we'd be able to do the electrical, then the PCB, then the mechanical, then assembly and test. We'd be able to do it in series, but this is not how the real world works. Here's more how the real world works. Everything is done in line, and this is the actual fabrication process. So this is at the very bottom of the V. We've taken the system, broken it up into subsystems, broken it up into components, and now those components are going out and being actually built. So the design, the build, the PCB design, you can see how they're interacting with each other. Now, bidirectional design flow, that means that as there's design changes, we need to push them back. The back annotation provides a mechanism for reverse flow of information, whereby changes at any point automatically flow back all the way up to the top. If we're looking at the V design, these are the arrows that are going back across. And so we can have this process of going back and updating the requirements, updating the documentation, updating the tests to reflect this new flow. Okay, so let's talk specifically about PCB design for a minute. So here are some generic steps to do a PCB design. You're going to want to create and simulate the schematic from some simulation tool. A lot of these PCB design tools have a simulator built in. You might want to use PSpice. You might want to use some simulation package just to make sure that what you're building is going to do what you want before you go to the effort of building it. After you do that, you're going to want to extract the net list from that simulation tool, import it into some type of CAD tool. Now, like I said, a lot of these tools have all of this built into one design tool, but I'm talking about the generic steps. So Once you import it into the PCB, such as Eagle, there's often some cleanup that's required. Then you want to do the PCB mechanical structure. So this is including the layers of the PCB board, the ground plane, how many ground planes, how thick are they going to be. After you do that, after you design the board that you're going to put everything on, you actually do the parts placement. And it looks like you're just taking the schematic and dumping it on to this blank board. So parts are shown connected by wires. So not traces at this point in time. So when you drop it down, usually there is a graphical red wire that's kind of connecting the two parts together that need to be connected. So you place all the electrical components on the PCB and you start moving them around to get a design that you like. Once you get a design that you like, once you get all the components distributed nicely on the board, then you're going to start routing them together. So you take and you convert the wires into traces. So traces must be routed by inserting bins, and then vias. Vias go through the board to the other side. And then you can have backside traces. So in this way, you can take and run a signal and make it go through the board and across the board and back up, however you need to go to connect together the components. The tools have a built-in DRC, Design Rules Check. This is to check tolerances, and it's to check that no traces are too close together, too thin, etc. So run the tools DRC. And then you can add additional features. Topside ground planes, other copper regions may be manually added or poured into the design. Holes. How are you going to mount it? So you need to put in through holes. The silk screen, this is the text. Maybe you want to put a logo on the PCB board that's going to be drawn on top there. Maybe you want your team names, a revision number, a date stamp. What class is it for? Voids in the solder mask, if necessary for heat sinks or other reasons, must be cleared. So in other words, there's the solder mask that's down over the entirety of the thing, and then maybe you need to put a can over an RF component to keep the RF energy from seeping out. You need to remove the ground plane from underneath that, the solder mask from underneath that, so it doesn't short out when you put that can on top of it. Then you create the Gerber files and the drill table. These are files that are output from the PCB design software. The Gerbers and the drill table are then sent off to get the PCB fabricated. Now this can be done in one of two ways. You can use rapid prototyping. So if you want to go to one of the maker spaces, they have PCB design fabrication machines, and they'll etch the PCBs in real time right in front of you. Or we can send it off to a fabrication shop, and it takes some time, but usually it's about a week, and then they deliver back your board. So expedited delivery can double or triple the cost. Here's an example PCB. You can see a couple of the mounting holes that are on it, the components, the silk screen, which is the white lettering on it. When you mount these, consider the different standoffs. You can use nylon, you can use aluminum, you can use rubber feet to help reduce vibration. So consider vibration, damping the vibration. Is it going to be in a single place? Is this going to be flying in a UAV? Is this going to be mounted in a vehicle? All those have different vibration patterns, and you need to make sure to isolate your circuit and also any connections that are going to it, any wires that are running into it, need to be properly strain relieved and vibration protected. Power. Are you going to use battery or are you going to use power supply? Consider how big the device is. Batteries oftentimes make things more complex at this stage. So I would highly advise that initially, especially for your prototypes, just plug them into the wall. It's much easier. So doing that, you need to think about how much power the entire design is going to pull. Oftentimes you will want to assign power limits for each one of your subsystems. And as those requirements for those subsystems are developed, ask the people who are developing those subsystems how much current draw, how much voltage draw, what voltage rails are you going to need? And then take that into consideration in your hierarchical design so that you don't have 27 different voltage levels. You know what I mean? If you have one part that's requiring plus or minus 12 volts and everybody else is requiring 5 volts, is there some means that you can create that same effect without using the plus and minus 12 volt rails? All these are very important. Also consider the linear converters versus the switching power supplies. Switching power supplies are much cheaper, but they're a lot more noisy. So linear, they're really nice, but they're also a little bit more expensive. Heat dissipation from both of these are a major concern. So now, when you're going forward in your development of your capstone design projects, here are a couple of rules of thumb. Make sure you know how to use all the parts that you intend to buy. Read the data sheets. Some of these data sheets are massive. Sit down and read them. Oftentimes, the parts that you're getting, you might be getting just because you've used it in a prior class. But it might be complete overkill for this design. Look at the alternatives. Make sure your parts will interface together. Consider Bluetooth, Wi-Fi, microcontroller voltages and currents, protocols. So there's a voltage level that's called TTL. And then there's a low voltage TTL. You've got to be very careful when you're connecting things together because low voltage TTL and TTL are not the same thing and they will burn out one chip or the other. Begin with a small prototype. So don't start off by doing a 200-hour 3D print job in order to get this massive enclosure that includes mounting holes and everything. Even more general, no 3D printed boxes. They are too complex. They take up too much time. There's too high of a probability that something will go wrong. Instead of doing a 3D printed box, do a laser cut wood box. They are quick and easy, and if something goes wrong, you can fix it and redo it real quick. So try to be very aware of what parts you're going to 3D print and try to keep them minimal. So keep your early design options open for adaptation. Don't get so set down a single path that you can't adapt. Once you build your design, once you have some pictures, hand sketches of what you're going to build, step back and look at it and say, okay, does this actually make sense? And play devil's advocate with yourself and try to figure out all the parts and see why they're there. Simulate, breadboard, everything you possibly can. This will give you the most amount of information before you actually build your circuit. And then add circuit protection everywhere. So anything that you think you can protect, try to go ahead and protect. All right, so this is it for this initial slideshow presentation. If you have any questions going forward on this, if you have any comments on this PowerPoint, please send me an email, get in touch with me.